Both of these are going to have the exact same crystal lattice, so they're both going to be aluminum oxide lattices, right? Both have aluminum oxide lattice, and it should be Al3 plus is the charge on aluminum. And oxygen, we know what's the charge on oxygen. 2 minus, right? That's our oxidation state for oxygen. So when we make an aluminum lattice, basically all the spots that make up the cage that creates the crystal structure will have something like Al2, O3. This will be our aluminum oxide lattice, and sometimes you'll see this as a common name as well for a lot of these different types of lattices. And really the only thing that's different between these two lattices is they both have chromium ions in there, right? So they both have chromium 3 plus. But the compounds that make up the specific lattice, so you either have aluminum oxide or a silicate, is what determines the different colors of these compounds, right? So what we have is we're going to have something. So this will be, I believe, aluminum oxide. And this is going to be a silica type lattice, and we have basically a bunch of molecules that fill up and make our crystal lattice. So this goes on, for all intents and purposes, infinitely in every direction. We have periodicity in crystal structures, which just means that we have repeating units of the exact same thing, right? That's what it means for it to be a crystal. And all that changes between these, right? Both of these are going to have chromium ions that fill up these spots in between the lattices, right? So we have these chromium atoms that fill up these spots. And depending on where it is on the periodic table and what the electronic structure is for that chromium, it forms interaction with its lattice that it's inside. And if this is silica or aluminum oxide, that gives you a different structure or a different color for the different gems that you're looking at. And it's because what happens is these different lattice molecules, or the molecules that make up the lattice, they cause different deformations in the ion itself. And when you have different deformations in that ion, it affects the energy levels, and the energy levels affect how you interact with light. And so understanding a little bit about the electronic structure for these transition elements, you can do some very simple type calculations and get a lot of properties out of just a very simple understanding, right? So if you want to make a specific colored gem or dye or something of that nature, you can just basically estimate it by looking at what we're going to be talking about today, something called the crystal field splitting energy, or the crystal field energy. And this is just looking at how do these ions, these transition metals, interact with either ligands or crystal lattices, right? So in this case, we're interacting with a crystal lattice, but in the case of a coordination compound or a complex ion, we're looking at how does a single ion interact with other molecules, right? And so these transition metals, they hybridize their d orbitals to then make bonds with different elements, molecules, or in what we'll call ligands. And so if we were to draw the electronic structure for zirconium, or ZR, how would we go about doing that? So let's just review, because the reason that's going to be important is because when we look at the outermost electrons, now the d electrons come into play here. And the d electrons are what are going to be deformed by the surrounding molecules or ligands or crystal that's surrounding these ions. And so we need to understand how many electrons are then going to be in the d orbital for an element like zirconium. So if we're looking at the abbreviated electron configuration, what would be the abbreviated electron configuration for zirconium? ZR. If we're doing an abbreviated electron configuration, what do we start from? Yeah, it'll be the most recent noble gas, right? So if we look at zirconium up there, it's element number 40. We go backwards, 39 is yttrium, then strontium, rubidium, 37. The closest noble gas, or previous noble gas, is krypton, right? So to avoid drawing how all the electrons fill every single orbital up to the outermost ones, we just write the most recent noble gas to represent that electron configuration. Right, so we start with Kr, and that represents all of the electrons that fill up to that point, right? Because the electron configuration up to Kr is going to be the same for any element past Kr, right? Those are all the core electrons. Those, they're that involved in the chemistry of the elements. So usually we just write the abbreviated electron configuration. And then after Kr, what's the first energy level that we fill? What's the next principal energy level after krypton? Yeah, it'll be 5s, right? It's principal energy level 5, because if we look at the periodic table and we look at the periods, which is going down each row, we have 1, 2, 3, 4, 5 is where rubidium starts, and it's in the s block on the periodic table, meaning that we're filling up the s orbital right after. So that becomes 5s. And how many electrons can go in an s orbital? 2, right? So, and we still have 4 electrons left over to get to zirconium, so the first 2 go into the 5s orbital. Then after the 5s, what orbital do we fill up? The d orbital, right? And does anyone know what the d orbital is for this? It's 4d2, because the d orbitals always fill up one principal energy level lower than the highest s orbital. And this is just a consequence of the structure of atoms, right? Really, this is just for hydrogen atoms, but we extrapolate it to all the other elements on the periodic table. And so the d orbital fills up next. It starts at principal energy level 4, because technically, because of just the way the math works out, the 4d energy level is slightly higher in energy than the 5s energy level, right? So these are where the anomalies start occurring once you hit the d block. These anomalies start occurring where you're filling in different principal energy levels in what seems like backwards order. And then if we go up to the F block, so the F block are the lanthanides, which is elements 58, 59, all the way to thallium, uranium, 90 through 103. Those are F block. Those fill up 2 principal energy levels lower than the highest principal energy level for the atom. I know I'm saying energy levels a lot, and principal energy levels. Principal energy levels are just the periods, or the rows on the periodic table. And that's just the highest electronic energy level that you can fill for that atom, right? So that's the electronic quantum number. That is the one that's associated with the nucleus, the positive charged nucleus, and an electron existing around the nucleus of an atom. All right, so that would be the abbreviated electron configuration. And what's going to happen is when we surround this zirconium atom with different ligands or in a different crystal field, these d electrons, so does anyone remember how many orbitals are within a d sublevel? It'll be 10 total electrons and 5 different orbitals, right? So I guess that'd be a good chance to review, right? The s orbitals, right, they're spherical, they look like this. The p orbitals look like the infinity signs. And you guys will have a lot of this in this px, py, pz. You have a lot of that in organic chemistry, because s and p orbitals are the only things important for organic chemistry. And then the d orbitals, only draw a couple. Remember, these were the kind of like the 4-lobed, and it's going to be like in each direction, and there's 5 different orbitals. The orbitals are represented by the bars in the orbital notation, right? So we have 5. Here we have 3 for the p sublevel, and then s only has 1, right? 2 electrons go in s, 1 goes spin up, 1 goes spin down, right? In the p orbitals, you fill up each p orbital first with 1 electron. That's called Hund's rule, and then you start pairing the spins together. And so the reason that it's important to understand the electron configuration for these transition elements is because when we add, so I'm going to use a symbol delta here, right? We add some I don't want to say a word, perturbation, right? We add something that's going to affect the electric field around these atoms. That's going to cause these energy levels to deform in a different way, right? Right now, if this is all defined at some specific energy, right? They're all at the same energy, right? We see each orbital is at the same energy, which is why when you fill this up, you put each electron in each orbital first, and then you go back and pair them, right? If we're thinking about how much energy was required to fill up an orbital, it's saying I can put it in here or there, one there, one there, one there, and these all add the same amount of energy to the system. As soon as we add something that disturbs the system, the energy levels are going to do what's called a splitting, right? And this is, once you guys learn about quantum mechanics and you go farther on, this is pretty much how a lot of different things were determined for atoms. So think of part of things like Raman scattering or hyperfine structure, things like that. Those are all related to distorting the energy levels somehow, and then now seeing that there's a separation of these states. And so what happens is you add something like a ligand or a crystal structure that distorts these energy levels, and then they might deform into something that looks like this, right? So now all of a sudden, you have 3 orbitals that are going to be lower in energy, and 2 orbitals that are going to be higher in energy, right? And all that happened is you just added something that kind of messes with the electronic structure of the system. When we learn about electron configurations in general chemistry, usually learning about them isolated in space, right? They're not interacting with anything. They're just isolated, floating around in space, and this is how the energy levels behave in that scenario. In the real world, though, there's a lot of things that are interacting with your atoms, and they change how the energy levels of the atoms. They change the energy levels of the atoms, not just how the energy levels of the atoms behave, but they also change the energy levels of the atom. We'll talk a little bit about why you kind of get this splitting, and there actually is like an intuitive understanding, to that. Okay, am I good to go back to the previous slide? This is kind of just a reminder, right? And so does anyone remember how many orbitals an F sublevel has? I'm not going to draw the F orbitals at all, because those are terrible to draw. Right, these ones have 4 lobes, so I can start drawing them, and then F has 7, right? So F, I'll just write it up here, has 1, 2, 3, 4, 5, 6, 7, right? So they have 7 different orbitals that you can fill up. So F shells can have 14. That's where you go from something like 90 to 103, right? On the periodic table for the F sublevels. And those are going to be, they do have interesting chemistry, and a lot of people do study that stuff, but for most common chemistry, you're not dealing with things with F orbitals. They don't involved in the chemistry a lot. And usually, for anything that's not a transition metal, the d orbitals that aren't involved because they're not the outermost electrons. However, in the transition metals, right, those are going to be part of your outermost electron structure. So they're involved in the bonding and the chemistry of these elements. And so what about cobalt? What would the electron configuration for cobalt be? The abbreviated electron configuration. What's the most recent noble gas? Argon, right? So we're going to start from argon, and then we'll worry about the ionization in a second. All right, so we're going to start with argon, and then what comes after argon? What energy level do we fill?
S.
Yeah, the S, right? And which S is going to be? What's the principal energy level for that? 4s. And we put 2 electrons in that, right? Because we only have 1 orbital for S shells, and then there's 2 electrons that go in there. And then we have how many electrons left? 7, right? So we have 7 more to fill up, and those all go in what?
The D orbital?
Yeah, they all go in the 3D sublevel, right? And if we don't remember, there's an easy way to write this down. If you write 2s, 3s, 4s, 5s, you can go up to 6, which is where the principal energy number stops. 2p, 3p, 4p, 5p, and then 3d, 4d, 5d, 4f, 5f. If you follow the diagonal along this little pyramid here, it tells you what order to fill in the electrons, right? So we start off with 1s, and then we go from head to tail to the next arrow fills in 2s, and then head to tail to the next arrow across the diagonal, we do 2p, then 3s. Next head to tail arrow, we go 3p to 4s, right? And then, now this is where we see the first anomaly, where we're not, 1s, 2s comes next, then 2p, that all makes sense to us, right? That nothing weird happening. 3s, then we go to 3p, all right, everything still looks good. Then we go to 4s, and then this is where the first anomaly occurs, right? Because we start filling in 3d after this. And you can extend the structure to look after that as well. But now you see if we fill this up, we go 4s to 3d to back to 4p, right? So if we were to continue filling an electron structure here, we would put 4p after this. So this is a little, if you can at least remember to draw this pyramid and draw the diagonals, you'll remember which way to fill in the electrons here. Right, so the way we fill this in is going from, head to tail, right? And that's just an easy way. And again, the only reason that we're going over this is because, well, how many electrons we have in the d orbital is important for the properties of the material, for things like magnetism and its color, how the molecule interacts with light. And so this was for cobalt neutral, right? And if we want to go to cobalt 3+, what do we have to do?
Just take away 3 electrons.
Yeah, we just take away 3 electrons, right? We have a positive 3 charge, which means we remove 3 electrons. And so when we remove electrons from a transition element, does anyone remember how we remove them? It's usually, sometimes it's taught, sometimes it's not. But for transition elements, it's still easier to take away electrons from the s shell first. And so that's why you see certain other elements like silver and whatnot, they have weird looking electron configurations because the way energy works and the energy pairing of electrons with each other, sometimes it's easy, like this compound, for example, you could take one electron from the s and put it into the d orbital, and a half-filled shell and a mostly filled d orbital is lower in energy than just having the lowest to highest energy levels filled. And it's because of all the different considerations, right? Like usually when we're looking at those diagrams, we're looking at it in the vacuum of space, but in real life, there's a lot more other things that we're taking into consideration, right? So that's taking into consideration, well, how much energy is it to put 2 electrons right next to each other? Even if they're opposite spin, there's some sort of energy value associated with that. So usually when we look at the ionization of transition elements, we take away from the s or p orbitals first, or even heavy elements, not transition elements, but heavier elements on the p block. We take away from the s orbital first, and before we start taking away from the d shell. So this would become 4s0, 3d6, right? We take away s electrons first. And that's just because it's saying it's easier to take those electrons away than it is to take them away from the d shell. And again, this is all really just coming out from assumptions of the hydrogen atom that we extrapolate to all these other elements, which is why, the real life things are a lot more complicated than how physicists assume they are. Right? And so for bonding, so I don't know if you guys remember, but when we form our molecules or our molecular shapes, we use something called VSEPR theory. Does anyone remember what VSEPR theory stood for, or what it was, or what we used it for? Yeah, that was exactly what we used. It was basically a qualitative way that we describe the shapes that atoms make when they form molecules. And so we use this language here, hybridize, is really what VSEPR theory is. And so, for example, let's see, do I have another slide? Transition metal slide. This hybridization basically said that, well, when we form a bond with another atom, we don't just, take the p orbitals and overlap them with the p orbitals of another atom. What we do is we form a hybrid orbital. That other atom coming into the system deforms our s and p orbitals to make a new orbital called an sp orbital, right? And so an s orbital looks like this, and a p orbital looks like that. And let's say another atom comes into play and it deforms this to form a molecular orbital. it will form a hybrid of both of these, right? A mixture of both of these to form an sp orbital. So that was p and that was s. And so again, when you're going into organic chemistry, you'll learn all about hybridization. You'll be sick of it after the first couple of weeks. But the reason that we do this isn't because this is how quantum mechanics actually has the shape deforming. It does when we solve it numerically, but we can't analytically show that. But the reason we do this is because this helps us describe the shape, right? How does the shape of molecules, or how are they affected by the atomic orbitals of each atom? And basically, another atom comes in, the electrons go into this bonding orbital between them, and it hybridizes the existing atomic orbitals in the atom. And then these describe the shape. So for example, when we have 3 bonding pairs, that hybridization, basically 2 of the p orbitals and 1 of the s orbitals in the atom deform to give you 3 sp orbitals, right? So this would be for, like if we had, let's say, s plus 1p plus the other p orbital plus the third p orbital, this would give us, no, I'll just do 2. Just 2 of them. This will give us 3 hybrid sp orbitals. So this would be what's called an sp2 hybridization. And this gives us the structure of what a trigonal planar atom would look like, right? We have 3 bonding pairs here. And it's saying that, well, when 3 atoms come to mess with my original atom, these orbitals are going to combine to form these new ones. And now I have a bonding spot for each of my new atoms that have come in to deform my system a little bit, right? So this gives us the origin of the trigonal planar shape. And so VSEPR theory was kind of developed to explain the shape in terms of the atomic orbitals qualitatively, right? We're saying, well, I don't really know what it looks like, but I'm imagining that when things come together, it takes something with my original electron energy levels, it messes with them to deform them in a way that makes sense to make the shape that I'm looking at. And so with transition elements, we don't just have s and p orbitals hybridizing, which is all we're worried about in organic chemistry. We also have the d orbitals that then come in to hybridize as well, right? So once we have transition elements, now we have even more complicated systems because the d orbitals are inherently more complex than the p and s orbitals, right? So for d hybridization, so you can have sp3d, sp3d2, you're combining all 3 of these and then explain the shape. And these are the more complicated shapes that you guys learned, like seesaw, octahedral. Anyone else have any other ones? Square planar, T shape. Right? Those are the more complicated shapes that come together. All of these come together to form those shapes. But the shapes themselves you're familiar with because you learned all the more complicated molecular shapes in your first semester chemistry. Right? So that's where the hybridization comes in. And so with the transition metals, now we have to just consider the hybridization of the d orbitals when we're thinking about the shape. And now I've started to also, well, when you perturb the system, that affects the energy levels as well. So if we're in a crystal lattice, or we have other ligands binding to our complex ion, that affects the shape as well, right? So now our hybridized orbitals are going to be deformed, and that's going to affect the properties of the material, like magnetism and the color of the compound. Okay, and so the transition elements. Actually, I'll pause for a second. Is there any questions on that so far? Okay, so no questions. So we'll have plenty of time to talk about all this. But so, for example, we look at periodic trends. We usually kind of skip over the transition metals, say, oh, we don't really worry about those. We just kind of draw arrows going across because for most chemistry that isn't important. But they do have trends the same way that the non-transition elements do. Things like atomic radius, ionization energy, electronegativity. And so, if we look at the size of these atoms, we see that as we go down, or what should happen is as we go down the periods, the size increases, right? So as we go down, so this is like, if we look over at the periodic table right there, if we go from hydrogen, lithium, sodium, potassium, rubidium, cesium, the size should increase for the atoms, Why? Because every time that we go to a new row, we've added a new principal energy level, which means that we've just added another electron shell, right? As we add more electron shells, the atoms should get bigger. Does that make sense to everyone, right? We have our just 1s, so if we look at something like magnesium, we have 1s2, 2s2, 2p6, then we go to principal energy level 3. That new energy level expands, right? The electrons can't all just be condensed around the nucleus. When we add a new level or layer of electrons like an onion, right, it should expand out, kind of like Shrek, life's like, or what did he say, ogres are like an onion? I don't remember. But atoms are the same way, they're like onions, right? Every time you add a new electron principal energy level, you expand in size a little bit. And that's the typical trend. Transition elements, theoretically the same thing should happen, but we see as soon as we get to the period 5 and period 6 and period 7 elements, right? So if we look at yttrium, things starting at that, and actually where is it? Lanthanum and yttrium, that the sizes of those two periods there seem to be exactly the same. All right, so I'm looking at these two here. All right, lanthanum and yttrium. So this is period 5 is the green one, and then period, I should just write it on here. All right, so period 5, and then the red is period 6. So the atomic radius does increase as we go from period 4 up to period 5 and period 6. But then after that, it seems like it stays the same. And so the only anomaly that you see in the transition metals, right, also as you go across the periods, you see that the size generally decreases, right? We add more protons to the system. As we add more protons for a given onion shell, right, the more protons pull the electrons in tighter, so the atoms should contract. But the anomaly that we see right here is due to the fact that once you get to lanthanum, number 57, you start introducing the F orbitals, right? And once you start introducing the F orbitals, you go through what's called the lanthanide contraction, and this is going to be the reasoning for a lot of anomalies in transition metals. You go through the lanthanide contraction, and basically once you add the F sublevel, now you have to fill in the whole F sublevel before you're filling in the D orbital, right? Which means that if you're looking at element number 57, which is lanthanum, everyone see it, number 57 right there, it has the 2 stars next to it, right? La, lanthanum. After you fill in that D orbital, or that one orbital within the D sublevel, you have to fill in elements 58 through 71 in the F block, right? Which means that now you've added 13 protons to the system. It's the same trend as you go across the periodic table, right? You go across the columns, across the groups, or as you go from left to right. The atoms contract because you're adding for a given energy level, you're adding more protons, so the atoms contract. But when you go from period 5 to period 6, now you have to fill in all the F sublevels, which causes all the atoms to be contracted there, right? Now you're filling in an extra sublevel, so all the atoms are going to contract. So this is contraction, so this is a size decrease, or an expected size increase doesn't happen because we fill in F sublevel. And when I say the sublevel is, I use that interchangeably with the angular momentum quantum number. Right, so if we remember, that's L. L is just describes the shape of the orbitals. Right, so P is a sublevel, and that's represented by those infinity-looking lobes. Right, so we see an anomaly in the size because as we expand, or as we go from period 5 to period 6, we now have to fill in the lanthanides. We add 14 more protons to the system, which is like a whole row of elements. So then the size doesn't change when we go from period 6 to period 5 to period 6, or 6 to 7. Okay, so that's the size, the ionization energy follows a similar trend to the the ionization follows a similar trend to the atomic size, right? Once we get to the 5D series, right? Now we're looking at ionization energy. Does anyone remember what ionization energy represents or how we think of it?
How much energy it takes to make it like become an ion? Like,
Yeah, how much energy it takes to knock off an electron of the atom, right? And so generally we think, there's two ways we can think about it, right? If we go down periods, right, the size of the atom increases, which means the outermost electrons are farther away from the nucleus. If they're farther away from the nucleus, they don't feel that bond as strong to the nucleus, so it's easier to kind of knock them off, right? So cesium, for example, is easier to ionize than sodium. Why? Because the outermost electrons are farther away, they don't feel those electrical charge of the nucleus as much. We also have that as we go from left to right across the period, now we have a given shell, which is a specific distance away, adding more protons, those become closer to the nucleus, right? They feel the nucleus more strongly, it's harder to knock them off, which means the energy required to ionize that atom is larger, takes more energy just to punch off an electron. With the transition metals, it's a similar trend, right? There's more anomalies in here, and this has to do with filling of the electrons in different sublevels, and we're not going to talk about that a whole lot, but that's why, for example, platinum is a really good catalyst, because it can adopt certain electron configurations that are very low in energy. But the lanthanides, once we hit the elements that have to fill in the F block, their ionization goes up quite a bit compared to group 3 or period 3 and period 4, because now these atoms are smaller, there's a lot more nuclear charge for a given size, right? There's a lot more protons in there, so it takes a lot more energy to knock off those electrons. So they become harder to ionize once we get to the lanthanide contraction. And again, it's just the same idea here, that this is the lanthanide contraction that causes this anomaly. Right, so same idea, and like I said, most of the different trends that you see here, ionization energy, metallic size, and electronegativity, those are all going to be from lanthanide contraction is the reason for a lot of them. Okay, any questions on that for ionization energy? On what it means or... Right. Okay, and then electronegativity, right? These values are relatively small in general because metallic elements tend to do what when they form bonds with other elements? If you have metal in a compound, what is it? What kind of bonds do metals usually form? Ionic bonds, right? Which means they usually ionize and they usually don't pull electrons, they give them away, right? They usually donate electrons. So electronegativity is kind of a weird thing to think about for transition metals, but there is a trend for the electronegativity. And again, it's the lanthanide contraction that causes this increase in electronegativity for a given electron highest principal energy level, right? If we have the lanthanide contraction, right, these nuclear charges are going up, right? The amount of positive charge in the nucleus goes up. These atoms, these metals can hold on to electrons a little bit easier. Okay. All right, and then the transition metals, they also don't form just one type of ionic compound. They're called type 2 cations, or type 2 ions. I'll just type ions. Right, and that's because they can form multiple oxidation states, right? So they can form multiple oxidation states, which is why when we're naming them, we have to specify the charge on the metal in the compound. So for example, you can have iron 2 and iron 3. Manganese can form the most oxidation states out of any atom, right? You can have anywhere from +2 to +7 as its oxidation state. And that's all type 2 means, that they can form compounds where they have different charges, right? Whereas if we look at sodium, sodium is always going to be what charge on the periodic table? Positive 1, right? Positive 1, calcium is always going to be positive 2, magnesium is always positive 2. They only form one oxidation state. Transition metals are a little funkier, they can form multiple oxidation states. There's some exceptions to that, right? Like scandium, zinc, silver, those ones can only form one oxidation state as well. So there's like exceptions within the exceptions to the rule. And so the type 2 ions, again, these are kind of what makes them interesting, what makes their properties interesting as well. And so a lot of transition metals are also used as catalysts for different organic reactions, and it's because of their complex electronic structure that they're used for these purposes. Okay, so any these are basic trends in the transition metals that we're looking at here. Any questions on any of those or any curiosities? No? Okay. All right, so for the coordination compounds, right, basically what we have is a Lewis base that can coordinate to a central metal ion, right? So does anyone remember what a Lewis base was defined as? So this is from our discussion, acids and bases. Right, does anyone remember our 3 definitions of acids and bases? Or does anyone have an idea about how we defined at least one of the 3 definitions? If we can at least orient ourselves within one definition, maybe we can figure out what a Lewis base is. Yeah, Lewis bases, and we think that's in the Bronsted-Lowry definition, is we think of acids and bases in terms of accepting or donating protons, right? Arrhenius definition was, do we create OH minus or H3O plus in solution? Lewis bases we dealt with, and the way I remember it is I just think of Lewis structures, and Lewis structures I have to draw all those dots on them, right? It's the lone pair electrons that we're looking at. Do we donate or do we accept lone pair electrons? So Lewis bases are lone pair donors, right? So if we have something like ammonia, right, this is a Lewis base because it donates a lone pair, right? And if it comes in contact with water, it can donate that lone pair to the proton from the water and ionize it to make OH minus in solution, right? So they're lone pair donors. And so the way coordination compounds work is, well, now we don't just have these hybrid orbitals that are explaining molecular shape, but we have coordination of lone pairs to the hybridized orbitals of these metal centers. And so I've been using the term ligand, but basically what a ligand is it's a lone pair donor to a central metal cation. Right, so it's a lone pair donor to a metal, right? So that's just how we define it. They don't form a sigma or a pi bond that we're used to. They form these coordination type bonds to the d orbitals of these atoms. And so they're not exactly the same type of molecular orbitals that we're used to, or the hybridization that we're used to. They form these lone pair donor and acceptor bonds with these ions. That's why when we talked about acids and bases, that sometimes highly charged metal cations and things can be acidic because they can interact with water in this way, where they're accepting or donating lone pairs, which is how Lewis defined what an acid or a base is. And so these ligands can form complex ions, and this is just where we have an ion that is formed from a charged metal center and neutral or anionic ligands, right? So when we were looking at, for example, iron thiocyanate, this was one, right? This was an example of a, oops, sorry, that should be 2 minus. I think this is 4 minus actually. Of a complex ion, right? We have a positive metal center and then a Lewis base that coordinates with that, but overall the molecule is an ion, right? It's a polyatomic ion, the same way we think of like sulfate, nitrate, all of those are polyatomic ions as well. Except now we're not looking at covalent bonds, we're looking at these coordination bonds between the metal center and the different ligands. And we have 2 different types of valence. When we talk about this, the primary valence of the coordination compound is the oxidation number, our oxidation state of the metal. And the secondary valence number is the number of coordinated ligands to that metal center. Number of coordinated ligands. So again, we're using that definition of ligands. Ligands are just our Lewis pair, our lone pair donors to the metal center. And this is often called the coordination number. For the complex ion. So for example, if we were to look at the primary valence for iron, not thiocyanate, cyanato iron, we'll talk about how we name these a little bit. I don't expect you guys to remember all the prefixes and suffixes for everything, but I'll give you a table, and you just got to know the rules on how to name a lot of these compounds. So for example, hexacyanato ferrate, right, which is what this compound is right here. The primary valence for this, 4 minus, would be the oxidation state of the metal center here. Iron is our metal center. What would be the oxidation state of this metal center? Does anyone have an idea? I'll tell you that each of these cyanoions or Lewis bases has a charge of -1. Right, what's the total charge on this compound, on this complex ion?
Oh, it's iron 2.
Yeah, the total charge is 4 minus, right? So if each one of these has a -1 charge, the total charge that comes from this should be -6, right? But the total charge is -4, which means we need a +2 to cancel out, right? To end up with a charge of +4, right? So this would be a +2, which means it's iron 2, and then this is going to be -6, and overall we get a charge of 4 minus. So the primary valence would be +2, would be a 2 for this complex ion because that's the oxidation state of the iron. And then the secondary valence, which is the coordination number, is just the number of coordinated ligands. What would that be here?
E6.
It would be 6, right? Because we have 6 of the cyanate ions there. Right, we have 6 of them, so the secondary valence or the coordination number would be 6. And if you guys had to guess a shape for this complex ion, what would you guys think that it looks like? We'll talk more about shape in a little bit, but right, can you guys think of any polygons or shapes that have 6 corners? Okay, so if, huh?
I want to say it's octagonal actually, because I
Mhm.
just remember it saying 6 and it ends up being.
Yeah, that's a good way to remember. If you have 6 atoms bonded to a central atom, usually that means you're going to have an octahedral type shape, right? Metal centers are never going to have lone pairs on them, right? So that's going to deform the structure at R. This is going to form an octahedral structure, right? So we can start developing a little bit of an intuition. If this is our metal center, right, each of these are going to, this is how the different cyano groups are going to, or it's one of the ways that the different cyano groups can bond or coordinate with the central atom, right? And so it's kind of hard to see from my drawing here, but if this is like your x-axis, that's like your y-axis, and that's your z-axis, it forms the octahedral shape. So if we were to look at the different faces, right, it would have 6 different vertices. I don't think that helps at all. That goes there, that goes there. All right, so that forms an octahedron. And so really the only shapes that we're gonna see with complex ions are gonna be tetrahedral, square planar shape, and an octahedron, right? Because we don't have any lone pairs on the central metal atom because they like to be positively charged. So they're only gonna be forming non-lone pair shapes that you can have with your molecular shape. But that's just, we'll talk more about that in a second. That's just to kind of give us a little bit of intuition. But the secondary valence is the coordination number, the number of coordinated ligands we have. Primary valence is the oxidation state of the compound. And so we'll talk a little bit about the different types of coordination compounds, and we'll take a break right after that. So basically the way we can describe how they bind to our metal center is basically the number of ways or number of spots they take up on the coordination of the metal center, right? So a monodentate ligand is what we defined as only taking one spot or donating one lone pair. So for example, if we think about carbon monoxide, all right, which is a coordination, and it, interacts with an iron center and hemoglobin in your blood, which is why it's so poisonous, right? It actually coordinates better to the iron and hemoglobin than oxygen does, which is why when you get carbon monoxide poisoning, you suffocate because all of your hemoglobin ions are taken up with carbon monoxide. And so this only donates one lone pair. And that's because carbon monoxide looks something like this. We have a positive charge here, and then a negative charge here. And we just donate this one lone pair. That one lone pair is going to be donated to an iron. Right? So if we actually want to look at what iron, how it coordinates to both, right? So this is with oxygen atoms. The oxygen atom kind of has its lone pairs off to the side, right? And so this kind of coordinates to the iron and your hemoglobin kind of at an angle like that because of the molecular shape of natural forming oxygen. Whereas with carbon monoxide, you get something that donates the lone pair, and the geometry allows it to perfectly line up with the iron atom. So that's actually why it binds a little bit, not a little bit, but a lot of it better than oxygen does, and why it's so deadly free. So that's a monodentate ligand. What do you guys think an bidentate ligand is?
Takes up 2 spots.
Yeah, this is going to take up 2 spots on your metal center, right? So this is going to take up 2 spots on metal center, or donating how many lone pairs? Yeah, it should donate 2 lone pairs to your metal center. And so this is something like ethylene diamine. The abbreviation for this, which you'll see, is just EN. And what this is going to look like is if we have 2 carbon atoms, say they're binded to a hydrogen, it's going to be binded to an amine at one position, something like this. And each of these nitrogens here have lone pairs. So if you were to have a metal center, it'll coordinate to both of those lone pairs there. Right, so each lone pair takes up a spot on the octahedron. Right, so if it was like our shape was an octahedron, can't draw it very well. Right, but this is what it looks like that. The iron is in the center of the molecule of the shape, and each of the nitrogens in their lone pairs are taking up a different corner. Then they're connected by whatever the rest of the molecule. That's what a bidentate ligand is going to look like, right? It's taking up each vertices here, each donating lone pair. And then there's polydentate, which is just going to take up, I'm going to put this definition down here, takes up more than one or two spots, or donates more than two lone pairs to the metal center. So EDTA, which is going to have acetate ions in there, which is what the A stands for. I'm not going to draw that molecule because it looks pretty complicated. This one's going to take up 4 spots on your metal center. So more than 2 lone pairs donated. And these can be used a lot for what are called chelating agents. So if you guys have ever heard of like heavy metal poisoning, things like that, chelating agents are usually how you treat those. And they put in stuff that coordinates really well to these transition elements. And the idea is that, okay, instead of them going in and causing weird reactions with your body, if we can just kind of surround it with stuff that coordinates it really well, it'll kind of make the heavy metal inert, and then your body will just kind of naturally pass it through, right? So this is going to be high, or strong, coordinating ligands that are usually bi or polydentate. Right, so if you come up with something like ethylene diamine, let's say you have a heavy metal, let's say lead instead of iron, and you give someone a lot of ethylene diamine, then the ethylene diamine will coordinate all the lead in the body. This part of the molecule can make it relatively inert, so the body doesn't really see the heavy metal center, and then that body will naturally pass it. So these are different types of ligands based off of their coordination, right? How many spots are they taking up on the metal center? And so the shapes that I mentioned before that you kind of see with these complex ions, so in the next slide, I'll just leave it up and then we'll take a break, are going to be shapes that you've seen before, and they're not the complicated seesaw, T-shape, the ones that involve lone pairs on a central atom. These are all going to be shapes that don't involve any lone pairs on the central atom. And so really you'll see linear, right? Linear coordination compounds or complex ions, right? This is where you only have a coordination number of 2 or a secondary valence of 2. Doesn't affect the primary valence at all. You'll have square planar, right? So that means you're going to have 4 different spots taken up, or a coordination number of 4, right? So it's kind of hard to see in this image right here, but that's a flat square, right? It's like the square equivalent of a trigonal planar structure. It's a square. You'll have tetrahedral, which is going to depend on the type of ligand and metal center that you're binding to, and then octahedral, right? So if you have up to 6 ligands, then you'll have an octahedral structure. And so these are really the only geometries that you're going to see for coordination compounds. All right, so we'll talk about the naming when we get back. Let's take like a 10-minute break, and then we'll come back, go through the naming, right? For the final, I'm not going to require you to memorize all this. I'll probably give you these tables. It'll be more about, can you remember the rules and how to name these compounds. So when we're naming these complex ions, they just have different naming conventions as everything does in chemistry. As you'll see on Thursday and next semester and the semester after, organic chemistry has a lot of different naming conventions, right? So half the class feels like it's just learning how to name organic compounds. For inorganic compounds or complex ions, any ligand that ends with an "ide", so like chloride, fluoride, cyanide, all those things, they get replaced with O, right? So fluoride becomes fluoro, chloride becomes chloro, and so on, right? So these are going to be our Lewis lone pair donors, and those are the ones that end in "ide", right? So especially any halogen or any of the type 1 anions, so like oxygen, sulfur, things like that. Then you can have different ions or anions, ligands that end with "ate", originally like sulfate, sulfite. Those ones end, naming if it ends with "ite" goes to ito or ito, and then "ate" goes to atto, right? So for example, sulfate becomes sulfato, for example. And so that's just the way that these ions are named. And so like I said, I'm not going to expect you guys to memorize all of these different ions here. It'll be, I'll give you the chart, and then you're just going to remember the rules, which are going to be coming up. Neutral ligands carry their normal name with some exceptions. So ammonia becomes amine, water, or hydrogen or oxygen dihydride becomes aqua, carbon monoxide becomes carbonyl, nitrogen monoxide becomes nitrosyl, methylamine, so that's just another type of amine, and then pyridine. These are all different compounds. These just have unique names, right? So these are unique ligand names. But other neutral lone pair donors, so let's see if we had, benzene, for example, that can also donate lone pairs. That one would just be called benzene. So these are the good ones because they carry the normal name. The only ones that you'll probably see would really be carbonyl, aqua, and amine. I probably won't give you guys anything methylamine or pyridine, right? So those are a little bit more complicated. So these are neutral. They just carry the normal names, except some that have an exception. Polydentate ligands follows the same trend as as anions and neutral ligands. So ethylene diamine, that's the one that I was just talking. That's a bidentate ligand. Oxalato, so that's just going to be another big complicated molecule. And then, so ethylene diamine is neutral. And so that's why it just carries its normal name, whereas oxalate, the oxalate ion, that one gets changed to oxalato. So even though these are polydentate ligands, they follow the same trend. And then ethylene diamine tetraacetate, right? So that's why I didn't want to say the name earlier. Also, I didn't remember it. Ethylene diamine tetraacetate becomes ethylene diamine tetraacetal. And it's always funny when you have the prefixes like tetra and then something that starts with an A right after because they got two A's next to each other. What's the question called?
Oh, no, I was just confused. Acetal?
Yeah, acetato. I'm not exactly 100% because I've actually never heard anyone say these out loud because most people, most of these compounds, once you get to this level, they have their own common names anyway, so you don't really use the IUPAC naming, but this is the rules for the IUPAC naming. Oxalato, though, that's how you say that. It kind of reminds me of what are those creatures called? Oxalotl? Is that what they're called? Oxatl or oxalotl? Huh? The aquatic amphibious salamander looking things? Is it oxalotl or oxatl? Oxalotl. Okay, yeah, so it's like that. So you can think of those. I would remember polydentate ligand, right? They have lots of those little tendrils that go out, right? That's what the polydentate ligand does. Lots of those little tendrils that coordinate to the metal center. The multiplicity of ligands, so at least these are simple for the monodentate ligands, right? Those are the same prefixes that you know for naming covalent compounds, right? Mono, di, tri, penta, tetra, penta, and then hexa. For polydentate ligands, right? Mono wouldn't make sense because polydentate ligands only take up 2 spots no matter what. Bis, tris, tetrachus, pentachus, and hexachus are the prefixes, right? I'm not sure where those come from. I don't know why they had to change it for that. But that's the naming convention for polydentate ligands. And then metals use the oxidation state in their name. So if it was iron 2, you would say iron 2, but if it's iron 3, for example, the exceptions are for certain oxidation states, there is their Latin name that they go with. Again, I'm just introducing these to you guys. I'm not going to be expecting you guys to memorize all of the Latin names, right? So ferrate, cuprate, those are ones you guys are probably familiar with. Lead, plumbate, probably not as familiar with that name for lead. Right, so the metal ions are, there's a couple exceptions, but that's the same convention for naming ionic compounds. Basically, the way we name them is we list the ligands in alphabetical order using prefixes, but we ignore the prefix for alphabetical order. For alphabetical order. And then we just follow that with the metal, right? So we have prefix plus ligands followed by the metal. This is the general formula for how we name these things. So did I have an example? And then when we're writing the chemical formula, first, we just do it in the opposite order. First, the metal goes first, then the neutral ligands, and then so we have the metal, then we have the neutral ligands, and then we have the anionic ligands, right? So the chemical formula, and then we have the charge up here. Write that a little neater. All right, so they go in opposite. When you're naming it, you go in the opposite order as when you're writing the chemical formula. Right, so prefix, ligands, metal, in naming it in words. The chemical formula is metal, neutral, anionic, in brackets, and then charge. And these are funny because I wrote a space in between them right now, but in the IUPAC naming convention, there's no spaces between anything. So these are always fun to write because it's a jumble of 30 characters, right? You actually wouldn't have couldn't write a tweet with a lot of these names in there. Actually, no, it's not a tweet. X or a thread. I don't know. All right. So let's name these. So for chromium, that was one of our exceptions. So chromium goes to chromate because that is its Latin name. We have how many water molecules here? 5, right? We have 5. So what should the prefix for water be?
Penta.
Yeah, what does anyone remember what the ligand name for water was? Aqua, right? So it should be penta, aqua. And then what's our other ligand here? Chlorine, right? The chlorine atom is the other ligand. And then chlorine in its anionic form is called what?
It's chloride.
Chloride, right? Like sodium chloride is how we would name the ionic compound. But chloride goes to chloro, right? Anything with an "ide" ending turns to O. And there's how many of them? 1, right? So the prefix for that would be mono. So it becomes mono. Chloro, and then we have our metal, which is chromate, right? So the order for naming these compounds, following the convention we just used, goes something like that. Right? This is the Latin name. And again, the Specific ligand names and stuff, I'll give you a chart for that on your exam. Probably the only things I'll require you guys to know is if it's ide, it goes to O, if it's ite, it goes to ito, and if it's ate, it goes to atto, and then I'm not gonna expect you to know the Latin names. So if you put chromium there, that would be okay. All right, any questions on that name? Right, and so as you can see, this is actually a relatively easy one. You can imagine if we had the ethylene diamine tetraaceto on there, and let's say we had 6 of them, or not 6, let's say we had 3, it would be tris, and then writing that whole thing, it would be a very long name for one ligand on that molecule, right? So these look kind of funny when you do it. All right, what about the next one? What's our ligand? CN, right? So it's CN, which is cyanide, is the, right, this is cyanide, and when it becomes a ligand, it becomes what? Cyano. Yeah, cyano. And so this is actually a good one for us to remember just because you'll be using it a lot in organic chemistry, and it has the same, this is a cyano group, right? And also you noticed that on the table that there was also one that was, it said it was the isocyano, which is just the reverse form of cyano. We'll talk about that. This has to do with an isomer form of this ligand. And how many of them are there? 6. And that means the prefix should be what? Hexa, because what kind of ligand is this? Is it monodentate or polydentate? All right, if we think about, if we get stuck, we can think about, okay, let's see, what does the structure for this look like? It looks something like this, right? So what do you think? It'll be mono or polydentate? So you would think that maybe it would be poly, right? Because we have 2 lone pairs here, right? But the size of this is probably very small, right? If we were to look at something that maybe is like a square planar molecule, it fills up this whole square, right? This cyano group might be something like, something like that small comparatively, right? So it has 2 lone pairs, but it's probably not big enough to reach 2 spots on the complex ion itself. And so this is actually gonna be a monodentate, right? And what we can start thinking about now, well, is if it has 2 lone pairs, there's probably 2 different ways that this molecule can coordinate. And that's gonna have to do with the different types of isomers we can start seeing for coordination compounds. But this only has, it's a monodentate ligand, right? So we don't have to do hexachus. We could just say hexa, right? So it's hexacyano. That's the name, that's the only ligand we have here. So this becomes hexacyano. And then iron, does anyone remember what iron was? It was one of the Latin names. I'm not going to expect you to remember it. Yeah, ferric. Yep. Ferric. And then you notice for each of these, they're coordinated to some counterion. The fact that they're coordinated to some counterion, the reason that's there is just to tell you what the charge of the complex ion is here. So what do you expect the charge to be for this top complex ion?
Positive one? Or wait, no.
Each chlorine ion carries what charge? -1, there's 2 of them, so this is -2. So that means that for this whole thing to be neutral, the complex ion has to be +2, right? So it's the same idea with ionic compounds. These are what we just say are counterions here, just here to balance the charge. So this one, the complex ion itself on the top, is going to be 2+. And what's the charge going to be on this complex ion here? 3-. And then, if it was like, okay, what's the oxidation state of this metal here? If this is 3-, each one of these carries a -1 charge. What does the oxidation state for iron have to be such that the total charge on the complex ion is 3-? +3, right? Because +3 -6 gives us -3. All right, so we can think about, what you can get the information about the charge on this metal center just based off of the number of counterions that are bonded to the complex ion to make the total charge of the molecule neutral. right? But again, the naming convention, they're like I said, they can look a little funny, especially once the names because the names for this can actually get pretty long. Okay. Any questions on naming? All right, so next thing we'll talk about is structure and isomerization. Does anyone remember what an isomer is in general? So an isomer is going to have the same elements and same number of elements. Right, so an example of things that are isomers of each other would be, let's see, we can have something that looks like C4H8. And two ways that we could draw this molecule. Actually, I'll do a smaller one because that one's I'll do C3H6. We haven't talked about how to draw carbon skeletons. Two ways that we could draw this is we can draw these little triangle structure, a ring structure like this, or another way we could represent or this molecule could exist. 1, 2, 3, 4, 5. It could look something like that, right? So both of these molecules have the same elements in them, the same number of elements, but they look very different from each other. So these are what we call isomers. They have different bonding structure, and we classify these different isomers in different ways. And you'll learn plenty about isomers in organic chemistry as well. Those would be two examples of structural isomers of two organic compounds, right? So we have cyclopropane and then one propene are the two molecules there. And they're important because different isomers can have very different properties from each other, right? So if we look at, for example, sugars in your body, all sugars are one isomer. All natural occurring sugars are one isomer, and then non-naturally occurring sugars can be a different isomer of each other. One can be toxic for you, and the other one, your body digests just fine. So isomers are very important for determining the physical properties and chemical properties of a lot of compounds. Stereoisomers are things that can have different spatial orientation, meaning that you can have the exact same connectivity, right? So these are what we would call structural isomers. Stereoisomers can have different spatial structure, right? So they can have the same connectivity, meaning the same atoms are bonded to the same atoms in two different molecules, but they look different from each other. So which is even kind of more amazing that can affect physical properties by quite a bit. But if we look at the shape, it can kind of make sense, right? So these would be like structural isomers. Stereoisomers, for example, is if we have something like our ethylene diamine. Sorry, I keep forgetting to draw the carbons. We haven't talked about that yet. This is one way that we can draw this molecule. Let me draw the double bond a little, or the carbon atoms a little bit better. Carbon, carbon, carbon. Right, so we have both the amines on the same side of this double bond. Or another way that you can draw this molecule is you can have the amines on opposite sides, right? So here, they're both on the same side of the double bond, and here they're on opposite sides of the double bond. And so they're still the exact same, right? Like this carbon atom. this carbon atom here is still bonded to one hydrogen and one nitrogen. This carbon atom is still bonded to one hydrogen and one nitrogen. And it's the same for all the atoms, they still have the same connectivity, but the spatial arrangement of these two structures is completely different from each other. There's no way I could rotate this, spin it around to superimpose these two structures on top of each other. So those are what we call stereoisomers, right? So they have different spatial orientation, even though the connectivity is the same, right? So this would be different connectivity, which would be mostly related to linkage isomers, and this is different spatial orientation. And those fall into two categories. We have geometric stereoisomers, and then we have optical stereoisomers. The reason they're called optical is because so you'll learn about this in organic chemistry, chirality, and these things. Basically, these different types of isomers rotate light differently when they interact, right? So it affects the optical properties. How does this molecule interact with light? And then you can have geometric, where it's just the connectivity or the spatial orientation is different. So these would be considered geometric isomers, right? So these would be considered geometric isomers, and optical isomers are things that are going to be chiral, and they just interact with light differently. And that's why if you feel, okay, well, Chem 1B is too much math, I don't like it. If you like drawing things or visualizing things, picturing how things rotate and things like that, organic chemistry might, feel comfortable to you, because understanding these different structures and how they rotate in three-dimensional space, right? It takes a little bit of creativity to think about that. And identifying these different isomers is very important. And the different types of isomers you see are important for the types of chemical reactions they go through, right? That'll affect the mechanism of its, elimination of this double bond or something like that. And then for structural isomers, the ones we have are the different linkages, right? So here, this would be a different structural isomer. These would be different linkages, right? The connectivity is different and the types of bonds are different. And then the ones that we're interested for coordination compounds would be like coordination isomers, right? So coordination isomers, right? Both of these, are important for coordination compounds. Both of those are important for coordination compounds, but they're different. So coordination isomer is going to be a different orientation of coordination. And all that means was the example earlier when I talked about the cyanide ion, how it can coordinate. You can either have the nitrogen side coordinate to the metal or the carbon side, because it has a lone pair on it as well, right? So if we have an iron atom, it can coordinate with the cyano group, right, this way, or it can coordinate it with it this way, right? So the lone pair from the nitrogen can coordinate with the metal, or the lone pair from the carbon in this compound can coordinate with the metal. So those would be considered coordination isomers. The geometric isomers, like cis and trans, are going to have the same type of coordination, but it's going to depend on what's the spatial orientation of how these compounds are coordinated to the metal center. Oops, sorry. Right, so isomerization is really important for chemistry in general, and especially for organic chemistry. You guys will learn a lot about that. And so geometric isomers, things that are like cis and trans. So this right here is an example of a cis isomer. This is a trans isomer. It has to do with the fact that cis, they're on the same side of the double bond. Here, they're on opposite sides. With coordination compounds, they get a little bit more complicated, because if you have a square planar or a square planar structure, right, you have two ligands on one side, one on the other, and it depends on their relative orientation to the center of the square there. Okay. Any questions on this before I just kind of give you some examples. Right, so for the coordination compound stereoisomers, if we have square planar structures, so we have an example of square planar structure, we can have, let's say, platinum, and it's coordinated to 4 things, right? This is what's going to make the square for our square planar structure. And these will be cis or trans. And let's say we have 2 different types of ligands in each of these, right? We need some, for these isomers to exist, these stereoisomers, we need some sort of asymmetry or ways that we can arrange different things, right? So we'll have chlorine and fluorine ligands, 2 of each. So the chlorine in a cis structure, both of those are going to be on the same side of the square. And then the fluorines will be on the opposite side. So this would be a cis structure or cis isomer for a square planar molecule. If we have a trans structure, that just means, well, the only way we can really change this structure is if we just swap the places of one atom with another, right? So if the chlorine goes here and the fluorine takes a spot of that, then we would have what's called a trans isomer. So let's say we had fluorine here, and then the 2 chlorines here, right? The connectivity for both of these molecules is the same, right? This platinum is still coordinated to 2 chlorines in both of these, and 2 fluorines in both of these. But the 3D spatial arrangement is very different from each other, right? Like you can see it just by looking at that these are not the same shape in 3-dimensional space, right? Chlorine and fluorine atoms take up different spots in 3-dimensional space. So this would be trans. And so for square planar or tetrahedral geometries, tetrahedral is a little bit different. We won't really talk about tetrahedral isomers. But for square planar, this is how we determine cis or trans structures. If we have octahedral structures, they don't say cis or trans for those. It's FAC and MER. And so let's say we have something where we have 3 chlorines and 3 fluorines, right? We have 6 ligands in an octahedral structure. Let's say platinum only forms square planar structures, so let's say we have something like iron. It's going to coordinate to 6 different things. Try and draw these a little bit more symmetrical. Something like that. A FAC isomer is just going to have all 3 ligands on one face of the octahedron. All right, so what that means is our 3 chlorines, or fluorines we can say, will all be on one face. And the chlorines will all be on another face. And when I say face, it's just because, right, an octahedron is going to have 4 different triangles, right? There's going to be one triangle right there, another triangle right there, another triangle right here, and a triangle in the back as well. So there's going to be 4 different triangular faces. The vertexes of one of those triangles is going to have all the isomers on it, right? So for example, this triangle right there and this triangle right there, both of those have all of the different ligands on both sides. So that's what we call a FAC isomer. MER, we can think of like meridian lines on Earth, right? And while we can get one from the other, just by doing the same thing we did before, replacing or swapping a chlorine and a fluorine in these cases. So for example, if we swapped, let's say, this chlorine here, chlorine, and then chlorine. So all we did is we swapped I'll say it in a second, right? We swapped this fluorine with that chlorine, right? Now you see that they don't form on the same face of any triangle here, right? They don't have the same 3 ligands on the corners of each of these triangles. Instead of what they do is they take up the meridian lines of each of these like kind of if you thought about the iron as like the earth, right? They take up the vertical spots or the horizontal spots on the meridian lines, right? So this would be that meridian, and then that would be those. So that's called a mer isomer. And really the only thing I'd expect you to do for these isomers is if I gave you the chemical formula and I said this is a square planar structure, which you should be able to determine if it's square planar or not yourself, is then just draw the 2 isomers. You wouldn't know beforehand which isomer it forms, right? We're not looking at the actual coordination chemistry. You don't know which one's gonna form, but you should know that, okay, this structure and those 2, they're stereoisomers of each other, and I can draw them. And really the easiest way to draw them is you just swap one of the places of one of the ligands. Here, these are easy monodentate, anionic ligands, so they're kind of easy to draw. The other ones can be a little more complicated. But and again, these are the stereoisomers, right? They have the same coordination. These ones can only coordinate in one way. They have the same coordination and the same chemical formula and the same connectivity, but different 3D spatial arrangements, right? This structure has a different spatial arrangements of ligands compared to that structure. And I know it seems like, well, what's the point of this? Again, this changes the physical properties of the material by quite a bit. And you can get kind of more complicated examples if you mix in polydentate ligands, and I'll try to avoid giving you things like that. But for example, if we look at something like this first cobalt, I just want to show you what that could look like. The ethylene diamine, what kind of ligand was that? How do we classify this ligand?
It's a poly.
It's a bidentate ligand, right? It takes up 2 spots. So it takes up 2 spots, which means there's 2 of them. You take up 4 spots on the octahedron total, which means that'll affect the how many available chlorines there are or how many available spots for the chlorines to take as well. And so it's something that's going to be an octahedral structure because it's donating 6 or 4 different lone pairs, but it will also be a trans and cis isomer. So for example, you can have cobalt in both of these cases. We know it's going to have to accept 6 lone pairs because the ethylene diamine is polydentate. But the ethylene diamine can either be on the opposite or the same side of the cobalt atom, right? Because these ethylene diamines are actually connected by carbon atoms, right? So these are actually connected to each other. Each one of those represents an ethylene diamine. I was just going to draw all of these. And so in this case, right, the ethylene diamine is on opposite sides, and we can tell by the orientation of the chlorines that this will be a trans isomer. If they're on the same side, it would look something like the chlorine atoms, right? We can orient ourselves with the location, right? This would be a cis orientation for the chlorine if we pretended this was square planar. And then the ethylene diamine are going to have to fill in the rest of the spots on this coordination compound. Right, so now the ethylene diamines are on the same part of what would be the square planar structure, but it's octahedral because these are bidentate ligands. So this would be a cis isomer. And then for the nickel compound, you guys could do that one because we have 4 monodentate ligands, so that would have to be a square planar or a tetrahedral structure, but we haven't talked about tetrahedral yet. So that'd be a square planar structure. But again, for these, I would probably tell you the shape of the molecule, and then you just have to determine what are the different isomers based off of the chemical formula. The polydentate one, that one's a little bit more complicated. I probably wouldn't expect anything like that. But the general form for how these isomers look is, for octahedral, if we have 6 different ligands, it becomes a FAC N-mer isomer. And if it's square planar or octahedral with 4 different ligands, then it's cis or trans isomers. I'll go back to this. Okay. So we'll talk about probably the free response question that you'd most likely get on the exam, or what part of the free response question would be, is related to what we call crystal field theory, right? So now we're going to go back to talking about the hybridization of these d orbitals to determine the shape. And so what crystal field theory does, or as it suggests, you have a crystal field or a ligand field that comes in and it distorts the shapes or the energy levels of your metal center, right? So it distorts the shapes of the shapes of the energy levels of your metal center, and it causes the hybridization, right? We talked about how we get, for an sp orbital, we get an s and a p orbital that combine to make that little half lobe shape, and then for a linear atom, you have 2 different bonding partners, right? So 2 atoms there. So it makes bonding orbitals, or that describes the shape of it. For trigonal planar, right, you get 1 s and 2 p orbitals that come together to hybridize to form 3 sp orbitals. That's where the shape of trigonal planar comes through. For the more complicated shapes, like trigonal bipyramidal and octahedral, for example, you have now hybridization of the d orbitals that are included in there, right? So for these ones, it's no longer, right, this was just S plus P goes to 2 SP orbitals, right? When you add those together, a crystal field comes in, or a bonding partner, a ligand field that has its own electrical charge that distorts things. It distorts your S and your P to form those SP orbitals, right? And again, our S and P orbitals look something like that, right? So you're saying, okay, we're assuming that these just add together to form these weird shaped orbitals. Once we get to octahedral, we then add together an S plus a P plus a P plus a P plus a D orbital plus another D orbital, and that gives us then 6 sp3 d2 orbitals. Right, so it's saying you're adding all of these together to form 6 of these spd2 orbitals, which is why octahedral structures have 6 binding partners, right? Each one of those is one of these hybrid orbitals, right? The distorted orbitals. And crystal field theory is really aimed at understanding, how do these distortions actually affect the energy levels of the central atom. And so we then can think about not just how does the energy levels of the metal center get affected by these distortions, but what about the ligands that affects these distortions as well. And so we can have 2 different types of complexes or ligands, right? We can have strong field. So these are strong field ligands and weak field ligands for the 2 different complexes. And all this is related to is when we talked about like our d orbital, how it distorts, right? We distort it. This ends up, right, I drew this picture earlier. It splits the energy levels somehow, right? All that happens is that the size of this distortion I'm saying how big is this? Is this messing up with my energy levels? What the size of this energy gap between these states now? determines if it's going to be a strong or a weak field complex, right? So size of distortion, or size of energy gap, determined by strong or weak field ligands. All right, so how big this splitting of the energies is determined by whether the ligand that's coming in messes with things a lot or just messes with things a little bit. In kind of a visual representation of why you get this splitting of these energy levels, right? If we think about these are our octahedral shape, right? If we have, right, so each of these spots right here represents a ligand binding to our octahedral atom. If we have a ligand in one of those spots, right, these are the orbitals that line up along these axes, right? Which means that a ligand right there is directly trying to overlap with those ligands, or those orbitals of the metal center here. We're looking at orbitals of the metal center interacting with whatever our ligands are, the energy levels, right? So all of these in these top, right, they're directly on the axis with the bonded atoms, which means that you're trying to overlap these electron densities with each other. Putting an atom there takes a little bit of energy, right? Because there's already electron density there. Putting something else in a space that's already filled requires a little bit more energy, which is why now those that are on the axes have been raised in energy. Whereas if we look at the other d orbitals of the metal center, it's kind of hard to tell, but these are in between the spaces of each of the ligands, right? So these orbitals are filling up empty space, right? Not where other electron density is already taking place. So these are going to end up going lower in energy, right? Because they're not taking up empty space. These ones are going to end up higher in energy, the ones that line up with where the ligands are, and the ones that fill up empty space are going to end up lower in energy. So it's like the fact that these ligands have come into the picture now, they've influenced whether you're happier being on the axis with those bonding partners or in between filling up the empty space, right? So this is how the distortion happens, right? These ligands come in, they affect the electronic structure of your metal center, and they're saying, well, now it's easier for me to put the electron density in between the spots where the ligands are, instead of lining up with the spots as well. And so we'll continue next time talking about how this distortion, just based off the color of the solution, you can determine what the color of the compound is or what this crystal field splitting energy is, right? What is the value of this delta that I wrote here? And we'll talk about how that affects the spin of the complexes, right? And I'll give you a table like this on the exam as well. This is basically what are strong field ligands and what are weak field ligands. What's going to distort things a lot and what isn't, right? And so the fact that this energy level is there is going to change how you fill electrons in the electron configuration, right? Because you can imagine if you split the energy levels so much and you start filling this in, you're probably going to start pairing them before you fill in the higher energy levels. Whereas if this energy is really not that different, right? If it doesn't split it a whole lot, then you'll start filling in all of them before you start pairing electrons. If you have paired or non-paired electrons, that affects magnetic properties of the material as well, right? So these ligands, right? And I put ligands here, but these can also be atoms or molecules that represent your crystal lattice too, right? All of these things affect how the energy levels of these d orbitals change. All right, so we have that. We'll finish up next time, and then we'll probably get through all of organic chemistry next time. I'll probably condense that lecture a little bit. Last year was a little long, so I think this one's long, but this one's a little bit more interesting to me, so we'll go over that. All right, so today's lab, we're going to be synthesizing a coordination compound, and depending if the titration is set up, then we'll be determining the percent of copper or the concentration of our ligand based off of what it's coordinating to. All right.